So these days I'm about to finish my PhD, so I need to do the defense, and then I hope to be done this year. My main interests for work are actually spatial statistics or more general spatial data science. I did quite a few work on well, making Earth observation analytics easier and scalable. So I worked with data cubes, and also I spent some time working with array databases. I'm very much interested into applications in environmental modeling and monitoring, and web development is also very much fun for me, but I'm not doing that so often these days. So mostly I'm developing software in C++ and R these days, although I also have a background in Java and a few other languages. Okay, what's the aim of this tutorial? What I want to do is actually provide an overview of Earth observation data cubes, and I hope to make clear that you understand where they are useful and why. I'd like to give a demonstration on the gdalcubes library, which is one implementation of the data cube ideas I have been working on during the last 2 years or so. I'd like to present some applications of data cubes, especially on why they are useful to combine satellite-based Earth observation data from several different Earth observation missions. And then in the end, I'd like to discuss challenges and some ongoing developments, in particular regarding cloud technologies. So the tutorial is actually split up into 4 parts. So at first, I'd like to motivate the topic and introduce you to Earth observation data cubes in general. The second part will be an introduction to the gdalcubes library and R package. So I'll show some R code and also do some live demonstration, but you don't need to be an R professional to understand that. The third part is on applications of data cubes, which I am working on mostly, and this fourth part, in the end, we'll have some time for discussion, and also I give quick outlook on what current developments are going on. Good, so let's start with the introduction on Earth observation data cubes. The motivation of all is that as a researcher or data scientist these days, you have pretty good data and also pretty good methods available. So we have all these satellite imagery available mostly for free. Think of Sentinel-2, Landsat, MODIS data, but we also have a lot of analysis methods readily available. So there are all the machine learning methods that are available, but also more traditional statistical methods like time series methods. And in many cases, these methods are also available as open source software, for instance, as R packages or Python packages or so on. And for individual researchers or data scientists, it is not so easy to combine these two things. So the question then is, how can individual researchers apply complex analysis methods on today's satellite-based Earth observation data set? So for instance, imagine you have a cool method to identify abrupt changes in satellite image time series, and that is available as an R package, but you want to apply it on Sentinel data, which are large, and then you need to download the data and do a lot of pre-processing, and that's currently a lot of work. And this is one example where data cubes can be helpful to make this easier for researchers and data scientists. So as I mentioned, Sentinel-2 data is a good example. So what you typically get when you want to download data at the space agencies portals or at other data providers, even some in cloud environments, is a collection of files. So this is a collection of, I think, 102 Sentinel-2 images, and each Sentinel-2 image is a zip file, and then when you first see these files, you open the zip file, and then you're looking for the actual image data. And it takes a while until you really understand where the data is. And also, if you want to do time series analysis or process larger areas, that is actually pretty difficult because of data volume and also because of how the data is recorded. So the satellite flies around in orbits and collects, well, the images in these swaths, and then what you get is that each file has a number of, well, images or data sets In the Sentinel-2 example, it's JPEG 2000 compressed data, where each spectral band is represented by one file. But these individual images, then, if you want to combine them, that's pretty difficult because they spatially overlap. If they come from different tiles, they also may have come from different UTM zones, and the spectral bands have different spatial resolution. So some have 10, some have 20, some have 60 meter resolution, and that's actually why there's a lot of pre-processing needed to get something which is analysis ready. So another example I have, this is an example collection of planet scope data from Planet Labs. And even there you get one GeoTIFF file per image, which is pretty nice because you can just drag and drop it to your GIS. But then still, if you have hundreds of images, it's actually pretty difficult to organize them to do something like time series analysis. Right, so in the end, what we want might be something like this. So this is a very small subset of these data, but it's organized in a way that is, I would say, analysis ready, or even that you can visually inspect the images. So for instance, this is something like a data cube where the temporal resolution would be 1 month. So this is June 2019, this is July, and this is August on the right-hand side. And yeah, I mean, you immediately see what's going on. So the data covers some parts of the Amazon forest, and you see that there was a lot of deforestation happening these months. So the difficult thing in question then is how to get from here to there in the end. And that's unfortunately a lot of work. And let's just think about a few moments how ideally we would have the data organized. And that would be something like what I call the Earth Observation Data Cube. So the Earth Observation Data Cube is a quite generic term, and there is no common definition for that. But what most implementations actually agree on is that it's a multi-dimensional array, and typically that has spatial and temporal and spectral or variable dimensions. So in this example here, which I call an Earth Observation Data Cube throughout this presentation, is a 4-dimensional array. So you see these 4 cubes, but it's actually only 1 cube with 4 dimensions. So visualizing 4 dimensions is unfortunately always not so easy. So in this case, it's a 4-dimensional array with dimensions longitude or X, latitude or Y. Then we have 4 different time values. In this case, it's aggregated month. And then I have a variable dimension or band dimension with the spectral channels blue, green, red, and near infrared. So more formally, it's a 4-dimensional array where the spatial axes are aligned with the axis of the spatial reference system. So the whole data cube only has one single spatial reference system. That makes it very easy for analysis so that you can easily calculate distances between any 2 pixels or cells in the data cube. So these pixels or cells have a constant temporal duration and a spatial size. And in the end, every combination of band, time, Y, and X simply yields a real number. And that's something which is pretty easy to analyze, and all the programming languages or scripting languages that are available, they already have arrays as their fundamental concepts. So that is very easy, and that is something we ideally want to analyze and have the data in. So as I said, there is no common definition of an Earth Observation Data Cube available, but even the OGC is aware that there is a concept and the data cube is used as a term in the community, and there are a lot of different implementations out there. So the OGC recently came up with the Geospatial Coverages Data Cube Community Practice document. So that's, I think, not yet something final, what they published or so, but it's a draft document where they essentially list available implementations and, well, how they see data cubes as a concept. But of course, the concept of data cubes is related to other standards. Mostly, it's very similar to the OGC coverages concept. The OGC coverages, however, are more general. So they include data cubes, but they also include something like point clouds or general meshes. And then, of course, also the WCS standard is relevant for data cubes because it could be used, for instance, to access data cubes over web services. Then, of course, there's a WCPS standard, which is about processing coverages. So that could be seen as an interface how to process data cubes, although there's some kind of limited functionality in the standard, which, as far as I understand it, is not extensible. So there might be limitations in what you could do with the WCPS standard. And then, of course, I was very happy to learn about WPS in the morning, and also about the future development there, that it's also going into the 3.0 direction with modern JSON technology and standards similar to WFS3. So that's good to see. And of course, WPS is a very important standard which could be used to define processes on data cubes as well. So in this presentation, actually, I'm a bit more focusing on the question of individual researchers. How can I run custom Python, R, or Julia scripts on the data? And also how to build these data cubes from irregular satellite image collections. Because I think these standards mostly assume that the data is already like a cube, or it's available in an array database or so. But as I introduced in the beginning, it's not really the case when you download the data or when you access it on cloud environments. Okay, so let's see what is needed to create a data cube from these irregular satellite image collections. So the first thing we need to do is we need to understand the data product. And that's already something not so trivial as one might think. We have to understand the file organization, and we have to understand how do I get relevant metadata from the files. So how do I extract the date and recording date and time, and how do I extract other metadata, something like cloud coverages and so on, image masks. So the next step then is we need to define how our target data cube should look like. And so we need to think of the spatial temporal extent. What is our area of interest, and what is the time of interest we want to analyze. We need to define the resolution of the data cube. So which resolution do we actually need? So sometimes it's not really needed to work on full resolution always. So maybe for Sentinel data, 60-meter resolution is also sometimes fine for particular cases. Then, of course, we need to define a spatial reference system and the spectral bands we are interested in. And that may actually vary a lot depending on particular applications. Okay, so once we have defined our kind of virtual data cube, so the geometry of the data cube, so to speak, we need to filter all the images we have in our collection, and then only work with these images that intersect with the data cube. And then we have to batch process all the images and apply image warping. So that means they need to be reprojected to the target data cube spatial reference system. They may need to be rescaled, may need to be cropped, and that all involves spatial resampling. And that means that also a specific resampling algorithm must be chosen by individual researchers. So it can be by linear interpolation or by cubic, but it can also be nearest neighbor interpolation, and that also depends on the data. So for nearest, for say land use data where integer numbers represent certain classes, something like interpolation like bilinear wouldn't really make sense, but others may do. So that depends a bit on the data as well. And then afterwards, even when we have warped all the images to our target system, we need to do temporal aggregation because so images from different swaths, they spatially overlap, and sometimes they are just collected maybe one day after the other or 2 days after the other, although the actual revisit time of the satellite is something like 5 days or 16 days, depending on which satellite we look at. So that means, for instance, if I want to generate a monthly data cube, we need to combine the values from several images and then, for instance, compute the median, minimum, maximum, mean value or something like that. So this is how we can build a data cube from individual image collections. And the good news is that there are available tools that can do that. Most important, Gdal, the geospatial data abstraction library. So, and that is pretty good in reading data in a variety of different file formats and also in doing the image warping, the step 3 here. So it can reproject, rescale, and crop at the same time using the Gdal warp utility. And then, yeah, it can convert also from one to other data formats on the fly. What Gdal cannot do is really that combine data sets from several images that well. So it's possible, but it doesn't really understand time. So it will just, even if you will load a lot of data sets into one Gdal data set, so it's possible with these virtual raster data sets, then it would just mosaic them, but only create like one final image and not do the temporal aggregation in the end. So Gdal doesn't really understand time. And also not the organization of particular data products. For instance, the Sentinel-2 products, how different spectral bands relate to the files on disk. So it's something which you typically need to do on top and implement on your own in scripting languages such as R or Python or similar. So what is also important to know is that the data cube creation is needed to do our time series analysis or similar, but it's also not for free. So it involves a lot of computations and also it involves loss of information. So we apply a resampling algorithm and temporal aggregation. So that means we combine several images or several pixels to new values, and we can't really revert this step. And this may or may not be relevant for scientists. As a result, there's also not something like a correct data cube, because the data cube really is, well, the correct choice of data cube parameters depends on particular applications. So speaking about data cube implementations, there are quite a few out there these days, and they have different purposes actually. So for instance, there's the Earth System Data Cube, which is software and also running a service that primarily addresses the analysis of Earth system dynamics on global scale. So they have really brought a lot of different data sources in a single data cube, and the purpose is to analyze interactions between these different variables on global scale. Then there's, of course, the Open Data Cube project, which is Python-based, and there are a lot of national and continental scale deployments of these software. So there's the Australian Data Cube, for instance, where they put a lot of data only for Australia in the data cube, all the Sentinel data, for instance. And then it's more, the idea is really to have a lot of national or continental scale implementations where regional users can do their analysis. Then there's lower level implementation gdalcubes, which I will talk a lot about today. Then there's also a Euro Data Cube initiative, which I think is funded from ESA and running on some of the Copernicus DIAS platforms. And then, of course, there's also Google Earth Engine, which is not really doing data cubes, so they don't really produce data cubes, but they give users a data cube-like interface so that users can do time series analysis very easily. But they have all the image collections as a single object where you can then base your analysis on. So it's a bit similar to the data cubes. They don't do the temporal aggregation thing, but they give users very convenient access to the data, and it's pretty easy to use, and they have petabyte scale data. So that's pretty much a state of the art in terms of technology, and it's also the reason why a lot of scientists these days go to Google Earth Engine to do their analysis, because it's so easy and also free for scientists. So as I mentioned, they have different purposes, these different implementations, and also different properties. So for instance, some really do the creation of the data cube on the fly when you analyze the data. So for instance, this is similar to how Google Earth Engine works. You have your map view in the browser, and then if you write your analysis script, it will only calculate the pixels you actually see on the map. So, and that means that the data is actually not really changed, but processed on the fly. So all the reprojection thing and so on works on the fly, whereas some other data cube software pre-grids all the software. So they just define the data cube parameters on their own, and then they have pre-built data cubes to be processed by users. And that, of course, means that they don't have the flexibility to let users define the parameters of the target data cube. Of course, some of the implementations also have defined data cubes a bit differently. Some have like fixed dimensions, only 4-dimensional, for instance, whereas some others allow n-dimensional data cubes. So only 1-dimensional time series, 2-dimensional images, or 3-dimensional multispectral images, or even 4-dimensional multispectral, multitemporal space-time cubes. Some implementations so also support irregular labeled dimensions, so they don't have, for instance, really regular temporal intervals between subsequent cells, but they allow dimensions to be labeled and irregular. Then, of course, the availability of data cube operations and processing algorithms varies, and also the availability of programming language interfaces. And some implementations also allow to run user-defined functions over a subset or dimensions of data cubes. And so there's a lot of differences in the data cube implementations, but I think the core concept is essentially the same, that they all want to get multi-dimensional arrays readily accessed by analysts, because that makes a lot of things very easy. Okay, so that's what I wanted to talk about with regard to Earth observation data cubes in general. Now I'd like to discuss and present the gdalcubes library, which is, as I said, a rather low-level library. So it's a library and not a web service, but of course the library could be enriched by implementation on top to provide this as a service. So let's start. It's an open source C++ library interfacing Gdal, netcdf, SQLite, and some other system libraries. It is also available as an R package, which essentially wraps the C++ functions. The R package is available on cron, and that makes it a bit more accessible to data scientists and statisticians. The objective of the package and library is to make complex analysis of satellite image collections easier, more interactive, and if possible, also faster. And the library knows how to read collections from, for example, Sentinel-2, Landsat, MODIS, PlanetScope, and a few other data products. The data model is essentially 4-dimensional, so it only has 4-dimensional raster data cubes with dimensions space, time, and band, or variable. And it implements on-the-fly creation and processing of data cubes. You'll see what this means in a minute. So the idea is that the original imagery is indexed only, and that you don't need to maintain a second copy of the data. And as I said, the creation of data cubes is on the fly, so that means that it leaves the flexibility to apply the same analysis on different spatial temporal resolution, larger areas, and so on. So because it's on the fly, the reprojection and all the creation of the data cube, you simply can change parameters, something like the resampling algorithm or the spatial resolution, and then run the same script again, and it will work in the same way, but then potentially take a little longer for the computations. So the data cubes are lazily evaluated, so that means that you define a couple of operations on data cubes and the data cube parameters, and then only when you really want to plot the results or export the results to your hard drive, then the data cube is actually constructed and the processing starts. So then processing works chunk-wise in memory, so it takes care of your main memory. So it doesn't try to process the full data cube at the same time, but it distributes the data cube computations to smaller chunks and tries to parallelize as well at the same time. One thing I haven't mentioned so far in the data cube creation is that it's important to apply masks during the construction. So a lot of data products come with something like cloud masks or quality information per pixel. And it's important to apply this during the construction of the data cube before the temporal aggregation takes place. Let me go back to the slide on the construction of data cube. So what we want is that pixels that are cloudy, for example, don't contribute to the data cube at all. And so therefore it is possible to define masks before the temporal aggregation happens, so that these values are actually set to NA or missing before we, for instance, derive the median pixel values over time. Okay, I'd like to introduce some basic concepts of the library. One is the concept of the image collection, and that is a data model for satellite image collections. And that looks like this. So we have images, and one image has an identifier, just a name, a spatial extent, acquisition date time, and a spatial reference system. But one image may be composed from several Gdal data sets or files. And that is mostly the case, for example, for Landsat and Sentinel imagery, where you have one GeoTIFF or JPEG 2000 file per spectral band. So one image consists of a lot of several Gdal data sets. And then these Gdal data sets may refer to one or even more bands. So sometimes they have more than one spectral band. So for the example of MODIS, you have one HDF file that contains all the bands. So in this case, it would be just one Gdal data set that contains all the bands. And then the data model for image collections contains also some metadata per band, per images, and also on the collection level. So as I said, these data products are distributed in very different formats. So the example of Sentinel-2 is pretty impressive in that regard, because it has this complex folder structure where you really have to search for the actual image data for some time when we open it the first time. And Landsat 8 is an example which has a very simple format, I would say, where you just get a collection of GeoTIFF files in one folder. So in gdalcubes, there's the concept of collection formats, and these are actually a set of rules that how relevant metadata of the image collections can be extracted from the product automatically. And that includes a definition of the bands. And internally, that is a relatively simple JSON format with some regular expressions. So what we want is, we want to index all the images we have on our disk or in cloud storage, and just get one image collection out of it. So this thing here. And the collection format actually describes how the information can be extracted from the data. So that you can throw in a list of many, GeoTIFF files, for instance, and then the collection is automatically built. So this is documented, and there are a couple of examples available. And yeah, it can be extended in principle. Okay, good. So let's go on with the concept of data cube views. So I hope you can all hear me now better. Okay, so we've just learned about the collection formats that make sure that we know how to read the images and how to extract relevant metadata. So the next concept is the data cube view, which is essentially the data cube geometry and the creation options. So it includes the spatial temporal extent of our target data cube, the pixel sizes or the number of pixels per dimension, the coordinate reference system, and the spatial resampling algorithm and temporal aggregation algorithm used. So the concept of the data cube view is really just a virtual data cube, so to speak. It doesn't include any data and also not any information on spectral bands or variables. So that means that it is independent from particular data products. So the spatial resampling methods that are available include quite a few, essentially everything what Gdal can do. And the temporal aggregation methods also include some standard functions like minimum, mean, median, max, or sum of values. And then the regular raster data cube, what I call it in gdalcubes, is essentially exactly the 4-dimensional data cube we have just seen. So this is a data model of gdalcubes, 4 dimensions, and cells have the constant size in space and time. So let's look at a first very simple example in R. So what we have to do to process sentinel data. So at first we load the package with the library gdalcubes command. Then we just scan a directory where all the sentinel data is located. So, and we just get a list of available zip files. And then the next step is is to create the image collection, and that's only done once typically. So that gets a list of the zip files and the name of the collection format. So that's the magic string here that knows exactly how to derive recording date time of images and all that stuff automatically. So this scans all the files once, but doesn't read any image data. So it only, well, it opens the file with Gdal, extracts metadata, and closes the files again. And you only need to do this once typically. I can run this example live after this slide maybe. So then the next step is that we need to think about our data cube and define the target data cube geometry. And that includes the spatial reference system. In this case, we're just using Web Mercator for whatever reason. Then we define the spatial and temporal extent. So we use left, right, bottom, and top parameters here to define a bounding box in space, and temporal and limits here from June to August 2019. Then we define the pixel size. In this case, we just want to get a data cube with 30-meter spatial resolution and a temporal resolution of 1 month. And we use the average resampling algorithm, which makes sense because our resolution is actually lower than the original resolution. And we apply a median aggregation over time. So that means that if there's more than one image within a month, these values get actually well aggregated by the median here per pixel. And median is often pretty useful in time because it's robust against clouds and so on. So even if the cloud mask is not perfect, it can, in many cases, lower the influence of clouds at least. So that is the data cube view, and then we essentially combine the image collection with the data cube view, and then we get a data cube. We say we only want to read the bands 2, 3, and 4, so blue, green, and red, and then plot the thing and provide some visualization parameters. So let me try to switch to RStudio and do this live. So in addition, I say that I want to use 8 threads, up to 8 threads for processing here. So then I'm running, I'm selecting the files, and I can print the files here and also check what's the file size, for instance. And well, convert it to gigabytes maybe. And then I see it's 110 gigabytes I have here. So that's the same collection actually I've shown you in the beginning. So this folder with these 100 Sentinel-2 scenes. And then I'm defining the data cube view. I can print it, and then I get the information on the data cube dimensions. So for instance, I see that I have 3 values in the time dimension and 300 times 334 in space dimensions. And then I can run the thing, and then of course, oops, sorry, I forgot that. I forgot to create the image collection. So that's this thing I need to do once at the beginning. So it opens all the files once, creates the image collections, as I said. So that takes a minute or so. And then afterwards, I can just create the data cube, select only relevant bands I'm interested in, and then plot the result. And that then, of course, will also take a couple of seconds maybe. And then in the end, I hope to get a nice looking plot here. So yeah, and that's exactly the plot I have actually also on the slides in the beginning of the presentation. Right, so this is the example where it processes the data cube on the fly, so it doesn't do something. Even if I call this function, I only get metadata on the data cube. But it doesn't start reading any image data. And even if I execute it until here, I only get the metadata of the data cube, but it will not read any image data. It will only start processing all the things when I call plot or when I want to write it to disk later on. Okay, so let's go back to the slides. So yeah, that's the plot, what comes out. And the package can do a bit more than just plotting and creating the data cubes. It can also apply some on-the-fly processing of the data cube. So for instance, we have a function apply pixel that can compute or evaluate any arithmetic expression on band values per pixel. So that means that the apply pixel operation takes a function as argument, and that function receives all the band values from one pixel as arguments and then produces one or more values as output. So in typical use cases of this function are the computation of vegetation indexes, or these kind of things. Then the package also comes with a, let me just do it in full screen, with a fill time operation that well, does some kind of simple time series interpolation to fill missing values. The package includes a filter pixel operation that, similarly to the apply pixel operation, takes expressions and then sets band values to NA if they don't fulfill a logical expression. So the package can filter data cubes by a geometry and so that pixels that do not sect with the given input geometry are set to NA. The package can be used to combine data cubes that have the same geometry, and that is pretty useful to combine data from different sources. And it can also apply reduction over the space and time dimension, where users can, well, define reducer functions and that are then applied over the dimensions per pixel or per time slice. Well, select bands selects a subset of the data cube bands. We've just seen it. And window time can be used to apply something like moving window reducers or also some kernels over individual pixel time series. To extract data from a data cube, there are a couple of functions available in the package. One is query time series, where you just give the coordinate of one point, one or more points actually, and then you get the time series as a result. Query points is a bit similar, but you have to also the possibility to get the values at irregular space time points. That is also pretty useful for generating training data sets for machine learning classification, for example. And then there's a zonal statistics function that computes summary statistics over polygons. So yeah, what you see here is an example application of the zonal statistics function, which we just applied for testing. So, and here we derived the minimum, mean, median, maximum NDVI values over around 50,000 cadastral districts over North Rhine-Westphalia. And the data used were Sentinel-2 level 2A data for 1 year. So around 500 gigabytes, a little bit more. And then we aggregated these data monthly in a data cube at original 10-meter spatial resolution. And then after like a few hours, I think, of computations, we got actually the summary statistics per polygon here, which you see here in an animation. So that is actually quite powerful, I think. And also what is, of course, important if you want to process data cubes with other software afterwards, it's important to export the data cube somehow, and the package comes with two different options for that. One is to write the data cube as a single netcdf file. So you get a single file with 3 dimensions and bands or variables as netcdf variables. And the other option is to export a data cube as a collection of geotiffs or cloud optimized geotiffs files, where each time slice is essentially one geotiff file. And then, of course, there's a plot and a function available, and similarly an animate function that creates animated GIFs from plot, actually. So these data cube export functions, they support compression and also packing. That means that you convert the double precision floating point numbers to smaller integer types by applying offset and scale. So very simple transformation, but that of course loses precision, but it gives you the possibility to save some disk space in the end. And these data are then ready to be processed in external software or also with other R packages. So one concept of the package is that you can chain data cube operations. So in this example here, I'm creating a data cube, select band 4 and band 5. This is a Lancet data set. That means red and near infrared. I'm using the apply pixel function here to compute the normalized difference vegetation index. And this is a formula for the index. And then I'm using this as input to the reduced time function, where I then afterwards apply or calculate the median NDVI values over time for all time series independently. And then I plot the results using a color scheme and a specific number of of classes for the visualization, and with a legend, and then I get something like that here as a plot. So, and this is, I think, yeah, pretty nice because it allows to formulate chains of operations in a very simple manner using this pipe function here, which is, yeah, kind of a modern version from R. Okay, so some of the operations, as you see here in the apply pixel function, they actually expect functions as strings. And the reason for that is that these expressions directly translate to expressions in C++. So they are built in and they can be compiled in the built-in C++ library. But in many cases, you want to define more complex operations. And that can be done by providing user-defined R functions as well. And in this example, I'm similarly calculating the NDVI, but then don't apply a median aggregation over time, but instead apply a user-defined R function. And this function gets one pixel time series and all the bands as input, so a 2-dimensional array, and it returns one or more values as output. And in this case, I'm accessing the one time series here in this R function, converted to a data frame here, and just apply a linear model and return the slope of the regression line that was fitted to all the time series. So that would be a very simple, naive way to calculate something like the trend over time of the NDVI values. And then I plot the result, and I see here in the result that, well, at some regions tend to brown or tend to become more brown, so the NDVI gets lower, whereas some regions also became greener during the 5 years starting from 2014 in this area. Okay, as I've mentioned, so the data cubes are actually created on the fly, and that makes it relatively easy to go from low resolution experiments. So when you first want to explore your data, you do things on low resolution and just try out things with very simple algorithms maybe. But then in the end, if you played around a bit and want to really evaluate the model or the method you have on higher resolution, it's very easy to change this, because you then just need to change the data cube view and only the data cube duration parameters, so spatial resolution, only changing one number, and then apply your script again. And then this, well, of course, needs some more time. So we tried that out and had an example. We used Sentinel-2 data again, so that was approximately 90 gigabytes. And we derived the median RGB values over all pixel time series at different spatial resolution, and then measured the computation time. And we started with a pixel size of 300 by 300 meter, and then the computation took 40 seconds, so which is, I think, still okay for like trying out things and working more or less interactively. And then if we decrease the pixel size to 50 by 50 meter, the computations took 26 minutes. And then if we really go to the original resolution to 10 meter spatial pixel size, the computations take 2 hours. And I think that makes it quite useful to try out things first on lower resolution, and makes the work with a large Earth observation data in R a bit more interactive, at least. Okay, so I've prepared a couple of other examples which I'd like to share with you and try out live in our studio now. So let's switch and try out things. So the data I'm using now is a Landsat 8 data set. And this data set I try to show you on my hard disk. So it's actually on my external hard disk, and has actually 180 Landsat images. And one image, as I said, is just a collection of 10 geotiff files plus some metadata. And right, so I'm indexing all the files first. So I need to create an image collection again. So that means I'm interested in all the geotiff files. I'm just listing all the files here, which is 1,800 files now, because we have 180 images and 10 bands. And then this sums to around 271 gigabytes. And then, as I said, I first need to compile these images into an image collection. And before that, I need to find out whether there is a so-called collection format that understands the data. And luckily there is, so we can print an available image collection formats here. And that includes a lot of Sentinel, MODIS, PlanetScope, but also Landsat data and some climate data as well. So in this case, we need L8 SR, which means Landsat 8 surface reflectance data. It's level 2A data. And then we can create the image collection. And again, this is typically done only once, and opens all the files once and then extracts metadata only. And internally, this is actually stored as a simple SQLite database on disk, which takes like around 5 kilobytes per image. So it's not really something which takes, well, it takes a lot of space on your disk. So then the next step is to define a data cube view again. So in this case, we have actually data over 5 years, I think. And well, we just want to get an overview and define, well, 2 different data cube views. In this case, we'll just specify a spatial bounding box again, define the temporal range of interest, define that one data cube cell actually takes 1 year, and within 1 year we apply median aggregation. So that means if we have several images in 1 year, we apply a median aggregation, and derive the median values there. We use the pixel size of 100 meter only to reduce computation times for this tutorial here. And then we can try out things again. So we have this data cube view. And then we also want to define a cloud mask here. And for the Lancet data, they come with the so-called pixel QA band. And then you need to be a bit careful and study the product handbook and see what actually the band means and what values are okay. So in this case, the handbook said that these values are clear conditions. So no clouds and other things we don't want to have in our data cube. So that means that we define a mask band here. So this is the band and this is the values that are okay. So we need to invert the mask because these values are okay. So if they would be clouds or so, then we would not need to invert it. And then we can just, well, define a nice color scale using the color space package, which is quite nice in R, and create a data cube and apply the mask at the same time. So that's the third argument here in the raster cube function. And then we have a sequence of operations here we are doing. So we select bands 4 and band 5. We apply a pixel operation to calculate the NDVI. And then afterwards we filter pixels with NDVI less than 0.7. So that means that if this expression is not fulfilled, band values will be set to an A. And then we can execute it and plot it. So that takes a while. Let's see, because of course now it starts processing everything on the fly. And then in the end, we'll see a relatively sparse data cube because a lot of forest area has been set to an A due to this simple NDVI filter here. So let's wait a few more seconds until the results are there. Okay, so now it starts plotting. So sometimes also plotting is quite some work depending on the number of pixels you have. So yeah, that's the result. I can try to make it a bit larger. And then let's see how it looks like. Yeah, so the blue area is actually an A values, and then the green yellowish area is the pixels that are still in the data cube. Okay, good. So similarly, I can just export netcdf files. So instead of this, I could simply write, instead of plot, I can simply write netcdf. And then the nice thing is that it realized that we just also already have created the data cube. And then we have a file test NDVI NC here, and then this, for instance, let me try to open the files again. Can be visualized, for instance, using QGIS. So let's open QGIS and then check out the netcdf files file. So yeah, and that has an NDVI as a variable. And then you actually see the NDVI data cube, which interestingly gets the different times as bands in QGIS. So it tries to compose a color, RGB color image here from the different points in time. So yeah, you see exactly the same values here as in R, and then you can, I don't know, you can do whatever you want to QGIS, adding background layers, whatever. Yeah. Okay, let's go on with the examples. I have one more thing I want to explain here is that these chains of operations can be rather complex. So in this case, I'm computing the NDVI values, interpolate time values by just, well, or not really interpolating, just filling missing values by repeating the previous valid NDVI values, and then compute differences of successive measurements at the same pixels, and then reduce over time by computing the sum. And this is actually equivalent to computing the cumulative sum and then extracting the last value. And then we get something like a simple trend analysis as well. So a bit similar to what we've done with the linear regression example, but now with built-in functionality. And also what you see here is that if I assign this to a value, it doesn't really do anything except that it knows what to do. So yeah, let's see what happens here. Right. So it has this kind of proxy object, and then internally it has the whole sequence of operations stored in a JSON graph-like object, which you can see here. And then only if you call really a plot, then it's evaluating everything and tries to plot things. Okay, I'll skip that for now. So instead, let's maybe do this example as the last example for the live demonstration. So in this case, I'm creating a composite image, which is something like the greenest pixel mosaic image. So I'm calculating the NDVI and apply a user-defined R function to find the time point where the NDVI has a maximum value. And then I'm returning the RGB values at that particular time. So that's something like the greenest pixel composite, and we can process it. And then get something like this, which looks very green. Okay, let's go back to the slides. And discuss some limitations of the software. And then go on with the applications of gdalcubes. So yeah, what we have seen is that quite complex analysis becomes possible if you apply user-defined R functions within gdalcubes. So in principle, you can use any of the R packages that are available and stream them to the gdalcubes and execute them. One thing I also want to mention is that the performance of the gdalcube creation depends quite a bit on the data format. So GeoTIFF is typically quite fast, but sometimes data products use something like netcdf files that are extremely compressed, and that can be then rather slow. So the data model in gdalcubes is limited to 4 dimensions only, and it also requires auto-rectified images. So for some data, such as Sentinel-1 or Sentinel-5, there need to be some additional pre-processing before they can be used with the package. And the package also, in principle, can be used in cloud computing environments, but this actually requires a bit more work, which I will discuss later in the discussion. Okay, so we have lots of ideas for future work, and that includes also an integration to, well, with OGC standards. So to provide functionality to export or gdalcubes as services, something like WCS or WMTS, but also to well, expose gdalcube operations as WPS processes. So that would be something which we would be very interested in, but it's of course a lot of work needed. Potential future developments also include Python interface, although we would need someone who's really familiar with Python to implement it, and to implement an OpenEO backend implementation. So OpenEO is a project we had here last years that tries to build a unified API to communicate with with cloud providers that do Earth observation data processing. And yeah, there are lots of ideas. If you have further ideas or questions or want to contribute, so let me know and get in touch with me. So I'm also very interested in applications of the packages, of course. Speaking about applications, so yeah, let's go on and see how data cubes can be used in practice. So I have three different applications here. The first two are aim at showing how data cubes can be used to combine data from different Earth observation missions. And the last one is some work we've just started. So let's start with the first example. So the idea is that we want to monitor vegetation with NDVI as our target variable, but we want to use as much information as possible. So, and therefore we use different data sets. So we try to use Sentinel data, Sentinel-2, level 2A, we try to use Landsat 8 surface reflectance data, and we try to use some MODIS data, in particular the MODIS 09GA product. And these data sets have fundamentally different properties. So for instance, the spatial resolution varies between 10 meter, 30 meter, and 500 meter for the MODIS product. But on the other hand, the temporal resolution for the MODIS product is daily. So chances are pretty high that if the Sentinel image, you have clouds, that maybe 1 or 2 days later, you get the cloud-free image from MODIS, although at a much lower spatial resolution, of course. And then the file format used is also very different. So Sentinel uses these JPEG 2000 images, Landsat is uses GeoTIFF, and MODIS is distributed as HDF4 files. And what we do is actually, just as an example, a very optimistic approach. We build 3 separate NDVI data cubes first and use the same data cube geometry. So that means we have seen in gdalcubes this data cube view concept, which is independent from particular data products. So we use this and create 3 separate data cubes first, and then we can easily combine these to a single data cubes that has bands from all the input data cubes. So we kind of stack the data cubes, and then we can apply user-defined function on the result data cube and iterate over individual pixel time series and select the best available measurement for each point in time. So in the end, we have a kind of a daily data cube where if Sentinel data is available, then we use a Sentinel NDVI value per pixel. If Landsat is available, then we use Landsat. And if only MODIS is available, we use MODIS NDVI value. So that's, of course, assuming that the measurements are comparable, so that the NDVI measurements are kind of in the same range. But I think it makes clear that this becomes very easy with data cubes. So at first, as I said, we've just created 3 separate data cubes. And this is the area of interest here, which is somewhere around Münster in Germany. We use a 300 meter spatial resolution here for now, just to explore things. And we have 3 different data cubes and try to count how many valid observations, how many non-missing values do we have in our area of interest. And on the left, you see the Landsat 8 surface reflectance measurements that are that range around 10 measurements in total. We have a few more Sentinel observations, of course, around 30, I would say, in average. And then we have up to 80 MODIS observations available, depending on where we look at. So the idea is then to combine these data cubes, and then in the end, the result could look like this. So of course, there are days where we don't have any observation at all from none of the satellites, but sometimes we may have MODIS, but not Sentinel, and sometimes we even may have Sentinel. So of course, then the spatial resolution is very poor if we don't have Sentinel or Landsat data, but anyway, it might be better to have something than nothing. So that would be very interesting. So that's, as I said, a very simple approach to do this, but ideally we could look at longer time series and then, for instance, kind of learn the relationship between the different NDVI observations when we have data from all satellites at the same day, for instance, and then use some advanced machine learning methods maybe to relate measurements to the other. So that would be kind of interesting to really combine observations from different satellites. Okay, as a second example, we don't look at the same target variable from different data sources, but at different variables. And then the idea is that we want to analyze correlations between these different variables. And what we in particular do here is we combine vegetation, precipitation, and soil moisture observations from different sources. So we use MODIS 13A2 observations, that is 16 days product at 1 kilometer spatial resolution with vegetation indexes. Then we use data from the Global Precipitation Measurement Mission at 0.1 degree spatial resolution with daily temporal resolution, and soil moisture data from the ESA Climate Change Initiative with 0.25 degrees spatial resolution and daily temporal resolution. And then we just try to analyze how they variables may interact. So we have a very simple example again here. So how the approach is to build 3 separate monthly data cubes with the same geometry first. So again, the procedure is that we use the same virtual data cube geometry, build separate data cubes first, and then combine them to a single data cubes with bands from the different input data cubes. And before the combination, we apply some individual pre-processing to the data cubes. For instance, for the NDVI, vegetation and soil moisture data cubes, we calculate anomalies from the time series. So what we do is we build a long time series and apply some time series composition. So it decomposes the time series into seasonal, season and trend components. And then we analyze only the reminder component. And for the precipitation index, we calculate something like the standardized precipitation index, which is kind of a drought indicator if values are pretty low, but it's pretty good standardized and a very standard method for in hydrology, I think. And yeah, that's the pre-processing. And then we have 3 different data cubes with NDVI anomalies, soil moisture anomalies, and precipitation, standardized precipitation index. And then what we do is we can apply something, statistical tests for temporally lagged correlations. So is there any correlation between the variables in the time series available? And this is just an example result we've just created for testing. If you look a bit closer to it, so what you get here is actually, for instance, here it's NDVI and standardized precipitation index with time lag 0, and then a p-value for tests for 0 correlation. So that's a statistical test. And then, yeah, if it's 1, it's actually pretty likely that there is some kind of correlation. And then you can see the correlation estimate in this figure here, for instance, and then you get an estimate of the correlation coefficient. So that's, of course, a very simple example, but if you look really close to the data, you can actually see that in some forest areas that there is kind of interaction between these variables. But of course, there are much more sophisticated methods to identify these interactions, especially if you think of machine learning methods to yeah, find causal effects in time series. So that's something which is very interesting and also very, at least very easy to apply if you have a data cube. So the third application we're working on these days is with a colleague from Vienna. We want to do crop classification with so-called dynamic time warping. Dynamic time warping is a method that originally comes from speech recognition. And the idea is that we provide patterns with typical dynamics of vegetation indexes or spectral information over the year for different crop types. And then we try to find the most similar pattern in the real time series. So we kind of match our provided patterns in these examples for soybean, cotton, and maize, and we try to find the most similar one for our available data and per time series. And this function is actually pretty advanced, I think, and it's available as an open source R package, which is pretty good. But of course, then we kind of need to apply it to larger areas. And yeah, what we currently trying to do is that we apply this on Lancet data from 1997 on national scale in Brazil and South America. So, and then this would like generate a very interesting data set, I think, with really yearly crop types from 1997 until well, today, actually. So, and then really gets interesting maps of crop classification. Okay, so let's come to the discussion and an outlook of gdalcubes in general and also of the gdalcubes implementation. So I have, I think, 3 more slides where I wanted to discuss certain things. One is more applications of gdalcubes. So the examples I had here were actually very simple, but I think they kind of give you an idea what's possible there. So I'm very much interested into applying really complex machine learning methods on gdalcubes, because I think gdalcubes also make the application of machine learning methods much easier. So as I said, as an example, so something like finding causal effects in multivariate Earth observation time series would be very interesting. But also applying spatial temporal statistics is it's a very interesting area, which is sometimes needed depending on the data. So because sometimes you, or often actually, you have spatial temporal autocorrelations in the data, and if you really do statistical analysis of interactions, you need to take this into account. And in general, I would say gdalcubes are very well suited to time series analysis, or to the combining data sets with different properties, as we've seen in the applications, and also to processing larger areas. And the gdalcube representation makes it actually very easy to apply complex analysis methods. But on the other hand, we also have to be aware of that the content of pixels, although the gdalcube is actually technically analysis ready, that the content of pixels does matter. So we still rely on the quality of the cloud detection and atmospheric corrections. And our methods that we apply on gdalcubes needs to consider these non-optimal pre-processing. So for instance, in Sentinel data or Sentinel-2 data, with the provided cloud masks, you often still have like the border of clouds, which is not completely filtered out or masked out. So we definitely need to take this into account and well, need some robust methods that can deal with this. Yeah, another thing I'd like to discuss is that there are quite a few cloud-based platforms these days where to do your Earth observation and analysis. And for individual researchers, it's actually not so easy to choose one platform. So one option is, of course, using the Google Earth Engine. Other options include other cloud services, but sometimes it's also maybe possible to do the processing locally or at the university's computing center. And well, finding the most efficient tool or platform is not something that is very easy, I find. And that involves a lot of criteria. So for instance, the availability of data and algorithms is quite important, of course. Then for cloud-based platforms is of course the cost. So that's also one reason why many researchers go to Google Earth Engine, because it's easy and it's free for scientists. But then it's also important, well, what programming language you can use to interface with the platform, and also how much effort is needed for re-implementations. So if you have a fancy time series method and want to apply it on data, if the method is not there and you need to re-implement it in a cloud platform, that sometimes may be more time consuming than just downloading the data and working locally. So that depends a bit on what method you want to do, and also on at what scale you run your analysis. So maybe if you just have a few terabytes or so, but a very complex method, the most efficient platform is actually the local computer or the local computing center at the university. So that depends a bit on particular applications. And for cloud solutions also, it's a trust that is important in long-term existence. So you really don't want to change often the platform, of course, because that's much work needed. Yeah, for some of these things, actually, I'd like to mention the OpenEO project. I think there was a presentation about it last year at the conference. And that kind of addresses the programming language interfaces so that you can actually have a unified language that can connect to many different Earth observation analysis platforms, which is pretty useful. So as I said, so for gdalcubes at least, it's of course possible to work in the cloud. So the good news is that many cloud platforms already include Sentinel, Landsat data, and more. And gdalcubes relies on Gdal to read the data. So it's and Gdal can read directly from cloud storage, so that's not an issue. But sometimes the data is not really in a cloud-ready format. So, and that means that it's a bit time-consuming to do the analysis, or that you need to transfer a lot of data before you can actually run the things. And also sometimes the data organization is not so easy to follow. So for instance, sometimes you get just CSV files with links to the actual imagery. And in this regard, I just want to highlight two very promising technologies that are more and more used, which is the spatial temporal asset catalog stack. And that provides easy data discovery with modern JSON technology. And also there's Stack API, which is a RESTful WFS3 compatible API for searching stack items. And that's very useful for satellite image collections because you can really efficiently find the images that intersect, for example, with your study region. So that's a very cool development that makes cloud processing a bit more fun. And also the cloud optimized GeoTIFF file format is a very promising technology because it's cloud native and it supports these kind of HTTP range requests. That means that if you query only small parts of a file from cloud storage, you don't need to transport the whole file, but really can only extract parts of it and transfer it to your computing environment. And the good news here is that more and more providers actually offer access to cloud optimized GeoTIFFs. And that includes also, I think, at least one of the Copernicus DIAS platforms these days. Okay, before leaving some time for questions, I'd like to summarize. So I think we have seen that Earth observation data cubes facilitate the extraction of information from larger irregular satellite image collections. And we have also seen that data cubes make it relatively easy to combine data from different satellite-based Earth observation missions with different properties such as spatial resolution, temporal revisit time, and all that stuff. But we've also seen that the construction of data cubes is actually not so easy, so it's complex and it involves spatial resampling, reprojection, and temporal aggregation. These parameters are important for applications. And yeah, we've seen, looked a bit closer into the gdalcubes library that's open source and includes an R package. And this can be used to facilitate the analysis of satellite image collections such that you don't need to invest a lot of time in pre-processing the data on your own. So if you're interested in other DataCube implementations and so on, there is one special issue of the Data Journal. There are a lot of papers about Earth observation data cubes and also, well, a lot of different definitions of data cubes. So that's very interesting to explore if you want to look closer into the issue. And also I have some more documentation of the package, including some more practical examples, and also code for the for the first two applications I've shown in this tutorial. So thank you for listening, and yeah, I hope to answer some questions now. So I'll just check whether there are some questions in.
Thank you, Marius. Thanks a lot. There's one question that came by Philip Gärtner. asking at what stage would you mask out clouds? Well, I think you answered it in the follow-up of the presentation, but maybe you can summarize it for an answer.
Yes, I would do it during the construction of clouds because if you look here, the problem here is when you have like one image that has clouds and you have not masked it out and you apply a mean aggregation, so that really contributes to the data cube values. And so the idea is that you set it to an A, the complete pixel to an A before you apply the temporal aggregation. And that's also what gdalcubes does when, I have it in my code actually, I think, during the construction. So you have this mask here in the raster cube function, which creates a data cube. And then you apply directly the cloud mask here. Yeah.
Okay, thank you. There's one more from Nick. In the first example, you mentioned about stacking data cubes. What did you mean by this?
Sorry, the question? Stacking data cubes?
Yeah, stacking data cubes. So what do you mean by this?
I mean, actually, let's go to this slide. So if we have like different data cubes from different image collections, but they have the same data cube geometry, that you can stack them into a single data cube by combining the bands. So, and this is a join bands function, which I'm using quite a lot. So the result data cube is actually the same geometry as the input data cubes, but more bands. So the spectral bands come actually from the different data cubes.
Oh, sorry. I had to unmute me. Can you hear me?
Yes.
Yes. Hi. Yeah. Thanks for the interesting talk. I have an own question, but I've seen there are two more questions in the question answer section. Ben, do you see the questions?
Yeah, we addressed them. You can put forward your own question.
Okay. One of the last slides in the discussion section, you yeah. I think some slide before you stated out some issues regarding the platform where to process the data, where you concluded that it would be more efficient to process local or on the university's environment. Are you familiar with the Copernicus data exploitation platform that has relaunched in the beginning of the year, I think in April, because it provides some processing environment and addresses all these issues you have mentioned?
Sounds great. So first of all, I just like to highlight that I'm not saying working locally is always the best thing. Of course, that has limitations. So
okay, yes, of course.
It depends on the use case. I mean, so the Copernicus platform, I think I haven't checked this year. No, I have to do. Sounds great.
Yeah, I think the Copernicus data exploitation platform has been started in 2015, but has relaunched in April this year, and it's very easy to get access to the processing environment. It's free. It's depends on the user category you are. I think you can get, I think, 8 CPUs. For virtual machines, very easy for 6 months. Yeah, have a look on it. It's very nice.
That's great. Yeah. So in any case, there might be situations if you have other data sources, like if you want to analyze planet data or data.
Yes, they have Landsat data too.
Okay, good. But then if you do research on, say, Venus data, which is also a very cool satellite that is kind of experimental, but pretty cool, then of course you would need to do it somewhere else. So I'll definitely check that out. Thank you.
You're welcome.
And there's a follow-up question by Nick. So if you are talking about statistical analysis or machine learning, can you integrate data from multiple cubes, or do I need to stack them first?
You need to stack them first. So they not, I mean, they kind of need to be aligned in space and time. So otherwise it's a bit hard to, well, to build the model actually.
Unless you have a model that's nicely distributed or can nicely distribute it across, I don't know, bands, regions, time spans. But yeah. Okay. Very good. I don't see any further question, comments, hands, whatever. So thank you, Marius, and thank you all for joining. This was the final tutorial for today. The conference continues tomorrow morning, and there's an icebreaker this evening, starting at 8 o'clock. You can also find it in the agenda. So looking forward to see you in some other session and discussion and talks and presentations. Thanks for joining. Bye-bye.
Bye.